Okay, so we're going to continue on in chapter 11, and now we're going to be looking at the last half. This is going to be chain drives. So chain drives and belt drives really have the very same function. They are going to transmit rotational power and torque slash forces from one shaft to another so that it is smooth, quiet, and inexpensive, okay, to actually do that. The biggest advantage, as we talked about at the beginning of this chapter, for both belt and chain drives is that they have the flexibility of center distances where gears don't have that. So really grouped together function-wise, gears, belts, and chains do very similar tasks or almost identical tasks, except in some cases, we find that there's advantages of using gears. Then we've got some advantages of using belts. And then now we're going to be exploring what and why would we use chains, okay? Now, chains are actually a combination of kind of some of the stuff that belts have and some of the stuff that gears have, meaning we're going to have that flexibility of center line. We're going to have kind of, if you would, a chain going around, which mimics a belt going over sprockets that have teeth coming up. So the teeth mimic what gears do. So again, it's like a nice little hybrid between belts and gears. They are low cost. They're very readily available. They're most often made, I mean, there are there are chains and sprockets that are made out of different materials, but predominantly in an industrial application, chains and sprockets are going to be made out of metal, okay? Now, because of their nature, we have the spoked, if you would, teeth coming up from the sprocket in between the spaces on a chain. And what that offers for us a more positive transmission of motion and forces and torques, meaning that there's no slip like there would be for belts. Belts actually, the slippage can be an advantage, and we design that in for where it's going to actually start slipping so that if there is an overload situation, the belt slips and it protects more expensive elements in the machine downstream. Chains, on the other hand, are just going to jam, okay? And there can be breakage of other elements that are going on, but they offer us a more efficient low speed application than what belts were. So for instance, belts wanted to run most efficiently at about between 4,000 and 5,000 feet per minute, right? And if we slow those down, most often those slower speed applications of what we're talking about here, transmitting motion and torque, are going to be for higher forces, higher torque applications. Okay, so chains get that done more readily. So they're more efficient at the lower speeds because of the positive transmission using the teeth in between the chain. They also have little maintenance. Now, they're not maintenance free because they do require some lubrication. Okay, belts did not require that. Okay, so in this case, we do have to keep an eye on lubricating because when we have chains, again, in an industrial setting, most often it's going to be metal on metal. We want to be sure that their life is extended, and using lubrication for that is important. And then they end up having a longer life than belts just because they're made out of steel, out of metal. They're just going to last longer, okay, than what belts are. Now, there are a couple different types of very popular chains, and those are going to be found in figure 11.8 on page 308. So the most popular configurations are going to be roller chain. Now, roller chain is actually these first three options that we see here. The one that we're going to focus on in this chapter is going to be just roller chain. Again, the vast majority of applications that do have chains are going to be exactly that. And you have seen these on things like bicycles. Okay, that's roller chain application. Roller chain is going to consist of two side plates, a side plate on this side, a side plate on the other side. There's a pin going through, and then it's going to be wrapped, if you would, with a roller over the top of that pin. Okay. And then up through the spaces between each one of those rollers, you are going to have the teeth of the sprocket coming up. Okay. So roller chain with a sprocket, very popular. Now, this is a single strand of roller chain. And then you're going to notice that we can gang them together with multiple strands. All right. The multiple strands here, you're going to notice that you're really just going to get a multiplication of the amount of force that you can run through. Motion-wise, it does not change, but it keeps a lower profile chain and a sprocket, but then it spreads out the transmission of any horsepower and torque over multiple strands. Okay. The next type that we have here, this is an offset sidebar roller, just another application. These are going to be used when we are going to be taking apart the side plates. We can then add different elements onto it to be able to maybe accommodate pushing things along a conveyor or moving product in a, a packaging equipment type of a situation. So they're used a lot in automation. And then the last one that we have here, this is called a silent chain. We won't be looking at any sort of application in terms of designing these, but these are, and you've probably seen these in places where noise is going to be an issue. So it's a kind of like a conveyor type of a system. I think if I'm remembering correctly, aren't these the type that we see on escalators, for instance? Yeah. Yeah, so that's going to be those, but we won't be designing for those, but another popular type that you probably have had interaction with. Okay. All right. Chain pitch. Okay. Now we've talked pitch from gears to belts to now we're going to be looking at it in terms of our chains. Now chain pitch is going to be the classification of the roller chain size. So back when we talked about diametral pitch for gear teeth, that was the size of the tooth. That was capital P sub D. Okay. And then there was pitch diameter. Okay. We're going to see that very same thing here. For chains, chain is going to have a pitch, capital P, just capital P. And then we are going to see that there is a pitch diameter on our sprockets. All right. So we have to be careful when we start looking at these quantities of knowing exactly what we're talking about. So if we look at the top of page 309, okay, the top of page 309 here, we see a single side plate for a roller chain. So this side plate, if we look back at the previous page, it's going to be one of these side plates right here. All right. And you're going to notice that the distance between where the pins would come through the side plate, which sets the distance for the center line of one roller to the next apart, is called the pitch. Okay. And how this is classified when we call out a number on a chain, for instance, it's a number of a chain. There's like 60, number 60 chain, number 80 chain, number 30 chain, number 25 chain. And we will see the standard chain sizes right down here on the following page on page 309. The column here are standard chain sizes, okay? You'll notice it's 25, 35, 40, 50, and so on, okay? Now, those numbers mean something. To figure out what the size of the pitch is, meaning how far apart are those two pins on our roller chain / on the side plates, we can calculate that from the pitch. So for instance, if we have number 80 chain, okay, the pitch is going to be 1/80th of whatever the number is. So for instance, we're going to take whatever the number is. So if it's number 80 chain and we're going to divide it by 80, okay? So 80 divided by 80 is 1. That would mean that the distance on a number 80 chain between the two pins equaling the pitch is going to be 1 inch. Now, if I go down to a number 25 chain, okay, do this calculation. Take 25 and divide it by 80. What is that size? Everybody should be getting a calculator of some form out and calculating 25 divided by 80. What do we get for a number? I'm going to pull the chat out. Anyone? 0.3125, okay? That would be the distance apart. That's 5/16, okay? That's going to be a 5/16 inch distance between the two sides there. So if I'm a number 25 chain as opposed to a number 80 chain, you can see that that equates to, you know, how large or small the distance is going to be between those, okay? Additionally, when we start talking about the chain and that pitch and how far those are apart, we turn the page back over here and we look at the sprocket, we are going to have to match up our sprocket to fit with the number chain that we're specifying for an application, okay? Now, by the nature of the sizes that we just looked at, the larger the number on the chain, the larger the chain is going to be, the bigger, chunkier the chain is going to be, which is also going to allow it to transmit more force and torque through it, okay? So for different applications, we're going to be interested in sizing the chain based on whatever the application might be, okay? Now, let me go back to my PowerPoint. I just want to kind of make sure I'm not too far. So we talked about the distance between the pins is going to be our pitch. It's going to be, it's going to equate to the size between the pins. So 120 pitch, as we see here, divided by 80th, divided by 80 is going to be 1.5 inch pitch. So again, the larger the number, the wider that's going to be, and the greater the power carrying capability is going to be as well. Now, let's talk a little bit about multi-strand chains. As we saw earlier, we can gang them together to gain more strength based on a lower profile chain. So if we go back underneath here on page 308, we saw where we had a multiple strand roller chain. Now, as we look here, this is 1, 2, 3 chains that are going to be together, okay? Now, unfortunately, if we size like a single strand, that's what all our charts are going to be based on, single strand. If we have a single strand and let's say we now go to 3 wide, we do not gain a multiple of 3 on the strength, okay? What we do is we gain a factor, and that factor is going to be expressed here in the table on page 310. If I have 2 chains, my multi-strain factor is going to be I gain 1.7 in strength. For a 3 strand, I get 2.5. And then you can see the corresponding numbers, you know, accordingly. Now, the reason that we don't get a 1-to-1 ratio, if you would, is because as we have these together, these literally are integrated so that those side plates on the inside are shared between the different strands. So we don't physically have 3 full strands in this case. We've got side plates that are shared between the 2. Okay, so we can't gain the same amount of strength because part of the strength comes from the tensile strength of pulling apart one single strand. Does that make sense? Okay, so keep in mind that if you do multi-strand, you don't get a 1-to-1 increase in the power capability that can be transmitted. You need to look at the factors on the table up here. Okay. So that's multi-strand. Let's go back over here. The factors. There we go. All right. Now let's look at sprockets. Okay. Sprockets are going to be the toothed wheel that is going to actually mate with the chain in order to pull it along. And this is going to be what's going to be mounted on the shaft and is going to do our rotating, if you would. The teeth on the sprocket are designed with geometry that's going to conform to going up in between and mating with the spaces in between the chain. So if we go back underneath here, this is on page 310, figure 1111. We see the teeth here for roller chain application. Now, notice a couple things. Number one, the width of the actual part where the teeth are on, this, you know, if you would, the spoked part, the teeth are on, those have to conform to the width between the chains. So again, we have to be sure we know that we are going to match up whatever the sprocket is to whatever the chain is. I cannot mix and match chain numbers to sprocket numbers. Does that make sense to everybody? Okay. just like when we had belts. The profile of the V-belt had to be the same as the profile on the pulley or the shift, okay? So, and because of that, chains are also going to be something that is going to be commercially available. So, just like with V-belts, just like with gears, inside any, if you would, size family, so whatever the number of chain is, you're going to notice that the number of teeth on the sprocket is going to be a little bit different. It's not going to be every single integer of teeth. So for instance, if we look at a number 80 chain here, see, scooch this over a little bit, number 80 chain, it goes from 60, 64, 65, and so on. Notice that it's not every integer number. So when we're designing a drive that's going to incorporate roller chain, we have to be sure that we're specifying the sprockets as part of that drive that are going to be commercially available values. Okay, so if you recall from when we did belts, we had to do a little bit of kind of going back and forth with numbers and testing out pairs to see if we could find something that was going to work with the commercially available values. Okay, so that's gonna occur as well. Let me go back underneath here. Oh, pitch diameter. Let's talk about that really quickly before we move on. The pitch diameter for a sprocket is going to be very similar to that of a gear. So it's going to be, I don't know if it's exactly at halfway between the top of the tooth to the root of the tooth or that radius on the bottom. But that is going to be the portion that actively is going to be engaged with the chain, and it's going to be pulling it around. So just like we referred to on a gear tooth, that was the effective diameter. Same thing here. That's where most of the power is going to be going through. That's where the power is going to be going through and the forces are going to be generated. Equation for pitch diameter is going to be at the top of page 311. Okay. So what we're going to be doing is we are going to be creating a little sheet like we did the last time we were together when we did gears, because there are some here. I think it's nice to have it all in one place when you're looking at doing problems. And so the pitch diameter, small d, remember there's pitch, capital P is pitch, and that is going to be the distance between the pins for this, if you would, the size of the chain. So pitch diameter is going to be that physical diameter on our sprocket, small d, lowercase d, which is consistent with what we did with gears. So it's going to be equal to the pitch. The pitch is going to be in inches per tooth. Now, if we go back to page 309, the pitch is going to be the distance between, you might say, well, isn't that just inches? Yes and no. It is. It does equate to a distance here, but it's per tooth. One tooth is going to fit up between those spaces on one side plate. Okay, so it's still going to be the same units as we had when we were looking at pitch for gears. So inches per tooth. So those would be the units for pitch on our sprocket. And then we're going to divide by sine times 180 divided by the number of teeth. So in this case, then our units end up being inches, and we'll look at that when we do our equation sheet. Once we kind of get done with this, I want to kind of go through things and then we'll create our equation sheet. And then we'll do an example. Okay. Now, let's look at chain drive geometry, okay? So we're going to look at figure 1112 on page 310, okay? And that is this figure right here. This looks very similar to the belt drive that we looked at the last time we were together. So on the left-hand side, we have the smaller sprocket. On the right-hand side, we have the larger sprocket. We would assume that, for instance, we would have the faster moving part of our drive on the left-hand side here where we have the smaller sprocket on, because most often, just like other drives, we are usually trying to slow down the rotational speed so that we can increase the work or the torque that we can do. So just as we've seen with gears, with belts, and now with chains, we would expect that on a drive, this is going to be our faster moving of the two that are, in this two sprocket or this two chain sprocket drive. Motor could be here. It could be an engine, a gas engine. It could be a turbine. That's going to be our input. notice that it is referred to as a 1. So our driver, in this case, is going to be the number 1, just like it was for belts. And then the number 2 is going to be the driven. So this would be like going to whatever the machine is that we're driving. So notice that we have rotational speed W1 on the left-hand side. We have number of teeth on the left-hand side, number 1, and we have D, pitch diameter, number 1. So this is all going to be our drive side. Additionally, we have this angle. Similar to belts, this is our angle of wrap, and that's going to be the engagement that we have with the number of teeth on our chain. Over here on the right-hand side, we're going to see the very same things. We're going to notice that our W2 is going to be that of the rotational speed on our driven machine. And then we have a theta 2, which is going to be the angle of wrap, the number of teeth, and then also the pitch diameter, okay? The other thing that we see on here is going to be our straight line velocity. So if you recall from gears, we called that the pitch line speed. In belts, we called that the belt speed. And now in chains, we're going to call it the chain speed. And this is going to be the straight line velocity value for the angular rotation that we have on our element. So whether we're looking at the driven side or the driver side, okay, we're going to have the same chain speed in both cases. Now, if we look over to the right, okay, couple things here. Number 1, as you can imagine, just like for belts, we were interested in center distance, okay? I want to make sure I have everybody's attention because we're going over the basics here. There's no reason to be trying to go ahead and work on homework or work on any homework right now that maybe you're trying to catch up on, okay? Please follow along because that's going to be your best chance of getting maximum points on the practice problems as well as in your assignments. So when we look here, just like we had for belts, there is a range for which is optimal for center distance. So for a chain drive, it's going to be 30 pitches, okay? That means, if you recall, when we go back over here, a pitch is going to be an individual length, okay? And so center distance, because of the fact that it's not so much about what the physical number is, it's about how many of these links do we stack up and how far they're apart in terms of those links. Okay, that's how they're measuring center distance. So 30 pitches, or 30, if you would, links, and it would equate to inches, but it would be how many of those there are, and as many as you want to be between 50 pitches. Okay, so somewhere in there is going to be the ideal center distance. Now, if you're beyond that, or if you're, outside of that envelope, you just don't want to be too far. Okay, this is going to be the optimal range. This is where you want to start with. Okay, so the designs that we do, because we're not necessarily given a center distance, you're going to be picking between that range. Then down here, you're going to notice that we have the length of our chain. Now, the length of our chain is going to be in terms of links, not in inches. And the reason we do that is because when you get chain off of a roll, like in bulk, you literally are going to count how many links you're going to be pulling off. So if you've ever gone to, for instance, Ace Hardware or True Value Hardware, and you need some chain to replace something, you're going to go back to their hardware section and they've got a roll of chain, and you literally are going to be, you don't measure, I need 2 feet of this. You're going to do it in increments of individual links. Okay. So it could be about 2 inches or about 2 feet, but you're only going to get off to the individual links. So we specify the length of the chain in links. Okay. Not in inches. Does that make sense to everybody? Because you're going to have to count how many individual links you're going to get off that chain. Then as far as center distance, once we know how many links we're going to be doing, then we get the actual center distance based on the individual links that we're able to get. So for instance, you're going to calculate based on a center distance that you chose within a range, and that center distance is going to be used down here. Then you're going to determine whatever those number of links are, and it's probably not going to come out to an integer number. Okay, so then what you do is you either round up or round down to the closest integer number of links, and then you recalculate your center distance. Okay, so really kind of the same process that we did for our belts. And then lastly, we're going to be calculating an angle of wrap on both sides. So we want to know how much engagement do we get around the perimeter of our sprocket with the links of chains on either side. So theta 1 is going to always be on our driver side. Theta 2 is going to be on the driven. And those correspond to the figure that we see over here on the previous page. Okay. Now, here's the calculation for that. And what it says here is they suggest that you always have, they suggest keeping the angle of wrap greater than 120 degrees. Okay, so you want to have at least that much engagement. Now, that's where your center distance makes a difference. So if you end up getting your center distance too close, that's going to affect the wrap that you get on either side. Okay, and that's where checking that angle of wrap it just makes sure that you get enough wrap to transmit the power and the torque that is intended for that size of a chain. Okay. All right, let me go back to our PowerPoint and see where we're at. We did angle of contact. We did these guys. Good. So now let's look at the kinematics of the chain drives. And this is going to look familiar as well. So you're going to notice at the top of the second column on page 311, we have a velocity ratio. So velocity ratios, as we learned when we were in gears, is when we have two gears that are in engagement with one another. How many times does our driven go around? Or I'm sorry. Let me see. How many times does our driver go around in order to get the driven to go around once? You remember that? Same thing here. We had this on belts, and we're going to do the very same thing here for chains. It's just that they're not up against each other, but we still want to know how many times does our driver have to go around to get this one to go around one time. Okay. And this is our ratio. This is our velocity ratio, or we called it the gear ratio at that time. Now, because we have teeth on our sprockets, we now can count the number of teeth as part of what we can use to calculate our velocity ratio. So this all looks very familiar. So we can get the velocity ratio by taking the angular velocity of our driver, which is going to be the higher speed of the two in the drive, divided by the driven machine. Or we can also set that equal to the pitch diameters of the driven to the driver. Make sure you see which one is the number ones and the number twos, because remember, ones are going to be the driver. It's on top here for our angular velocity because it's going to be the faster moving, the larger number on top. Driven is going to be underneath. But then it switches. Driven goes on top because physically the sprocket is going to be larger. That's going to be our bigger number on top. And the smaller number is going to go on the bottom. So the driver is going to go on the bottom. Same for the number of teeth. More teeth is going to be on that driven, and then the driver is going to be on the bottom. Okay. Now, the other equation that we have been applying since actually our velocity module, which was, I think, module 3. So we've done 3, 4, and now 5. We've been seeing this relationship of straight line velocity components. So this case, because the straight line velocity is going to be out at the perimeter or on the pitch diameter of our sprocket, is going to be now the speed of the chain, the straight line speed of the chain, how fast that's moving. It's going to be equal to the diameter of the pitch on whatever you're looking at. So notice here that if I'm taking the radius, which would be the pitch diameter of the driver divided by 2, multiplied by the angular velocity, okay, of that sprocket. So in this case, notice that the ones have to go together and the twos have to go together. So you cannot take the angular velocity of 2 and multiply by the radius of 1. Okay, make sure that those are together. Sometimes it's, you kind of get balled up in the numbers and it can be easy to just put the wrong one in the wrong place. So always check that. Additionally, this has to be, our W has to be in radians per, whether it's seconds or minutes. So we saw, I'm going to put or radians per minute. Okay. We saw when we did our belt speed, the standard units that we express that in is going to be feet per minute. We're going to find that same thing for chains. Chains are going to be feet per minute. So then we would have W instead of in revolutions per minute, which is probably what you're going to get or you're going to calculate. Then you're going to use it in this equation. You're going to put it into radians per minute. Okay. All right. Before we do that, I know there's one more thing I just want to discuss down at the bottom of page 311. At the bottom of page 311, there are 3 classifications for a drive, and it's based on how fast they're going. So if the belt speed ends up being less than 650 feet per minute in what we calculate for the belt speed above here, that's considered a low speed application. In that case, you don't have to worry about designing in any sort of lubrication, okay? Meaning you can just manually lubricate it every so often, okay? Moderate speed, on the other hand, something that's going to be running between 650 and 1500 feet per minute is going to be considered a moderate. And then you want to then design in a lubrication. Now, again, we are not at that point in the design process, but it's something to keep in mind. And then lastly, anything that's over 1500 feet per minute, you then need to have lubrication like on it constantly so that it doesn't wear out prematurely. Okay. So those are kind of the classifications of the speed. So now what we're going to do is we are going to be looking at the problem on page 11.3. But before we do, let's make ourselves up a nice little equation sheet to kind of bring together the things that we just talked about, okay? So if you would, get out a blank piece of paper. And what we're going to do is you guys have done this often enough with me, okay? I want you to create, I'm going to give you, I'm going to say 10 minutes. I'm going to give you 10 minutes to create an equation sheet. And I'll check back with you in 10 minutes. And I want you to pull out the elements from the chapter that you think are going to come in handy for these types of drive problems. So again, similar things to what we did for gears, to what we did for belts. Now you want to do it for chains. Okay. So I'm going to just, stop the recording for a little bit here. And then we will. So if I can have everybody's attention, let's look at the equation sheet to be sure that you have everything that you need. Okay. So it's kind of is a nice little review of what we talked about. So at the top here, my very first one is when we want to calculate the pitch on a chain. Make sure that that is going to be the number of chain. So that's going to be your number 25, number 35, number 80, number 60, whatever the chain number is, and you're going to divide that by 80. And that is going to give you units of inches per tooth or inches per teeth, if you would. Okay, so capital P is chain pitch. Lowercase d is going to be equal to that chain pitch divided by sine times 180 degrees divided by n, which is the number of teeth. Okay, so d is pitch diameter and n is number of teeth. So when we put our units in for pitch on top, inches per teeth or inches per tooth, divided by the sine times 180 over n, our units are 1 over teeth in the bottom. So the teeth cancel out top to bottom and our pitch diameter ends up in inches. Okay, we always want to make sure that we resolve our units. They don't go over this in the book, but you guys are required in your problems to do this. That's why we spend time on this. This again makes sure that when I'm trying to find units or I'm getting my final answer, if you end up with the right units unselected or uncrossed out, you know you set it up correctly. Okay. So any questions on those two? Because they did not put the units in there for those. So make sure you have those for each one. Then they had said that the optimal range for the center distance is going to be between 30 pitches and 50 pitches. Okay, that's just a nice number. If you don't have an actual center distance you're working in, you just want to pick something in between there. Then as we look down here, these equations get a little bit longer and you have to write them out. So just be sure that you have them correct. But for the length of the chain, this is going to be in terms of links, okay? In terms of links. So this is going to be then, you're probably going to get a link value that's going to be not an integer number, but you will then pick an integer number after that. And that doesn't have to be a certain number. Commercially available is literally pulling it off the roll and counting how many links are going through your fingers, okay? So that's going to be the length of the chain in links. And then you can get the actual length by multiplying by the pitch, right? If you wanted to. Then down here, you're going to notice that this is then going to be the actual chain center. So in a design where we don't have a center already identified for us, we pick a center first to determine the number of links. We find our number of links, and then we use that down here to calculate what is the actual center distance that we're dealing with then, okay? And that's the equation that we have here. L's are those number of links. The N's are going to be the number of teeth on each one of the sprockets. Okay. Then additionally, you're going to have that angle of contact or angle of wrap. Oh, I should put a note here. Must be at least 120 degrees, right? At least 120 degrees so that we get enough wrap to properly transmit the motion and the torque / forces that are there. Notice that the equations look similar, except that on our driver, we subtract the 2 sine blah, 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 blah. And on the driven, we add. So the operator is a little bit different. Okay. So I see some people are writing. I want to be sure that everybody has what they need here. I don't want to rush this because I do have a couple things on the back of this page now. I'm going to turn it over. Okay. Turning over, this is going to be our kinematics. So this is velocity ratio. This looks just like what we were using when we were doing gears, because now we have the teeth in here because we have physical teeth that we can count. So it works just like gears that way. And then the straight line velocity or the chain speed is going to be that familiar equation, radius or the pitch diameter divided by 2 times the angular velocity. But remember, we are going to end up with feet per minute as our final velocity. So that means that we will put our angular velocity in radians per minute. Okay. Any questions on the equation sheet? I'll wait till everybody stop writing so that I don't get too far ahead, because we will be using this for our example, which then you'll have to hand in for your practice problems. Okay. All right. If nobody's stopping me, I assume you have everything that you need here. Okay. So then what we're going to do is we're going to look at that example 11.3. This is at the bottom of page 311. Scooch this over a little bit. Okay. And the problem statement says here that we have a single strand roller chain connects a 10 horsepower engine to a lawn waste chipper / shredder, as shown in the following figure. So if we go to the following page here, this is the drive that we're interested in. Okay. So this is coming off of a motor or an engine, and then this is going to be going to the actual chipper itself. Okay. So input, this is going to be our, if you would, W1, and then this is going to be W2, right? Driver down here at the bottom, and driven is going to be up there. Okay. As the engine operates at 1200 RPMs, the shredding teeth must rotate at 240 RPMs. So notice it says must rotate. So that means we need to get this down from 1200 to 240. Okay, they're not giving us an approximate this time, right? The drive sprocket has 18 teeth. So they're telling us what the number of teeth are on the driver, which is off the engine. Determine the appropriate pitch of the chain. So that's going to be our number. So that's going to be the roller chain number. The number of teeth on the driven sprocket, the pitch diameters of both sprockets, and the chain speed. Also indicate the number of links in a suitable chain and specify the required center distance. Okay, so what I want you to do is, if we go back over here, we just read the complete problem statement. I want you to, at the top of your page, let me know what you're given. And don't worry about the equations just yet. We'll kind of go through that. I want to know what you're given and what you need to find. Okay, so start off with, your problem and how you would start this, and just list out the variables that you're given and their quantities with units, as well as what this problem is asking us to find. So this is example problem 11.3. You will be handing this in for your practice problems. So as we look at the problem, they gave us the engine having 10 horsepower. They also told us that the engine is going to be rotating at 1200 RPM. That is the driver. So that's going to be our W1 is 1200 RPM. It tells us that the chipper must rotate at 240 RPM. So that means that our W2 is going to go 240 RPM. And then they also told us that the number of teeth on the sprocket that's attached to the engine, so the driver N1, is going to be equal to, or is equal to 18 teeth. Now what they want us to find is, okay, what is the pitch of the chain, or what is the number of the chain? Okay, so it's going to equate to a number. So like I said, a number 80, number 60, number 40, whatever it might be. What's the pitch? What is the number of teeth on the driven part? What are the two pitch diameters of each one of these sprockets, D1 and D2? What is the chain speed itself? So this is going to be VC. And then what is the center distance and the number of links on the chain, or the length of the chain in links? Okay. So quite a bit that we've got to find here. Okay. Quite a bit that we have to find. So let's see. And we're going to kind of peek ahead. We're going to follow the book-ish. Okay. And we'll kind of look at what they find, and we'll, either agree, if you would, or understand where they got things from, or we may change things along the way. Just depends. So it says here, with a 10 horsepower engine driving the sprocket at 1200 RPM, it says we want to specify a 40 pitch single strand chain, okay, to be appropriate. Okay, well, let's find out how they got that. They used figure 1110. Okay, 1110. So let's go over to figure 1110, which is on page 309. We didn't reference this when we were talking, okay, because it just wasn't part of it. But this is where we pick out the actual size of the chain. That's going to be our pitch, our chain number, okay? So you're going to notice that the two columns that we have here, we have the size of the small, or I'm sorry, the speed of the small sprocket in RPMs, okay? And then over on the right-hand side, these are all what we call design horsepower. Now, for the problems that we have, we're just going to use the horsepower that's given to us. I think I explained to you before that when we start introducing more variables, meaning the types of applications that we have, both on the what we call the input, so on the if you would, the engine side, and on the output, it equates to how volatile, or the chance of jams or problems happening. And so then what we do is we adjust our horsepower number for that. This book doesn't do that, but when you're in design problems later on, you're going to see a very similar chart like this, but you will be calculating a design horsepower. And based on those factors, usually is going to go up. We're going to account for more horsepower, if you would. Okay. But in this case, we're just going to use the 10. So all we're going to do is we're going to find the speed of our small sprocket. We know that to be 1200 RPMs, right? So that's 1200. That's this line right here. Okay. And then we're going to find where 10 is on our list, which is right about there. So we're going to bring those two together. Okay. And right here, you're going to notice is where they are going to intersect. So then we look, what category do we end up in? And we ended up in the number 40 chain. Okay. So it's just the number 40 chain. So if we look here, we would say step number 1, and this would be from figure, and this was figure 1110. Okay. Our pitch is going to be 40. Okay. Now this is I should say, to do this a little bit different. This is going to be number 40 chain. And then we're going to divide that by 80 so that we get the actual distance that the chain is. So it's going to be the number 4 roller chain, but the pitch is going to be 40 divided by 80. It's going to be a 5 or a 0.5 inch pitch. Does that make sense to everybody? Okay, that's how we get that value. So that's going to be, if we look up at the top of page 309, the distance between the two pins on our side plate is going to be a 1/2 inch or 0.5. Okay. So it's number 40 chain, but that equates to a 1/2 inch pitch. Okay. All right. So let's go back to our problem, page 312, and let's see what they do next. So they got a number 40, number 40, which is exactly what we got. So we've got that one done. So we could put a little check mark in front of our P. Right. Now, the next thing that they want us to do is determine the number of teeth on our driven sprocket. Okay. Now, if we look at our equation sheet, mine is on the back side here. I can use my velocity ratio here because this is where, if I know what the angular velocities are of each one of my sprockets, I can then calculate the number of teeth. Okay. I want to be sure everybody sees what I'm doing here, because remember, when you hand in your practice problems, if you don't follow the formatting that we're doing here, then you don't get the points for them. All right. I want to make sure you have everything that you need, because then this also leads to how you're going to format your assignments. I still have people that are handing in things that aren't how we're doing them in class. All right. So trying to help you out. So we're going to use this equation right here, but we're going to set the W1 over 2 equal to N2 over N1. That's where we're going to start. So step number 2 is going to be getting the number of teeth. So we're going to say W1 over W2 is equal to N2 over N1. Okay. Now, in the case of the information that we have above, we have W1, we have W2. So we know both of these, right? We also know what the number of teeth are on our driver. Okay, so all we have to do now is solve for N2. So we're just going to simply multiply N1 up. So this is going to be N1 times W1 divided by W2 is going to be equal to our N2, right? So if I put those values in, the number of teeth on N1 is going to be 18 teeth. W1 is 1200 RPMs divided by 240 RPMs. RPMs cancel top to bottom. And my N2, what do we get? $90 teeth. Tyler got 90. Did anybody else get that? Yep. Okay. So this is going to be 90 teeth. Okay. Oh, we're going to put a box around that because that's one of the answers that we're looking at. And then we also want to do that up here. So we want to say this is equal to our pitch. All right. So N2 we've got. Okay. Now that we know the number of teeth on both our pinion and our gear, I shouldn't say pinion and gear, on our driver and our driven, right? We know our number of teeth on our input off of the engine, and then now we've just calculated this one. We can find both of these pitch diameters, right? So if we go back to our equation sheet, pitch diameter is going to be equal to the pitch from above, okay, divided by sine 180 degrees divided by the number of teeth, okay? So we are going to use that information that we have. So step number 3, we're going to do these pitch diameters. So let's do pitch diameter number 1. Going to be equal to the pitch divided by sine times 180 divided by the number of teeth. And this would be number 1, the number of teeth in that smaller sprocket. So our pitch on the top is going to be 0.5, and it's going to be inches per tooth or inches per teeth, right? Divided by sine times 180 degrees divided by the number of teeth on number 1, which is 18 teeth. Teeth cancel out, and we'll end up with inches. So my D1, what do we get for that value? Now, this is where it's important. I don't know how your calculator works, but Chris, yes, you got the same answer as I did. 2.879. Be sure that you can get this. How I did it on my calculator, I took 180 divided by 18, and then I took the sine function. I hit the sine function on my calculator. I don't know how that works for you. And then I took that number and divided it into 0.5, and you should get 2.879 or 2.88 like Chris and Ben did virtually, okay? Make sure you can get that. This is where these example problems help, especially when there's maybe equations we don't use all that often. And you might be like, well, how are you getting that? Well, it might be the order that you have to put it in on your calculator. Okay, make sure you get that number. Now we want to do that very same thing for D2. So go ahead and write out the equation. Remember, we're always writing our equations out in variable form. So make sure that you write it out in variable form first before you put any numbers in. I'm still seeing people do that. You guys have had me a couple times now. It's the second year. The rules are still the same. $14.327. Yep, that's what I got too. Make sure you can get that number. Excellent. Noble got it. Tyler got it. Awesome. I got it. So if we go back, we now have both of those diameters, right? Okay. Belt speed. I'm going to go back on my second page of my equation sheet. Belt speed is going to be equal to the radius of that pitch diameter times the angular velocity. Now, this is where you need to match up your pitch diameters with your angular velocity. So if you're going to use the pitch diameter from the engine side or your input, then you have to use the angular velocity that matches that. If you're going to use it on the output, then make sure you match up those. Okay. All right. So that means this is step number 4. Okay. Chain speed is going to be equal to, I'm going to use the ones. Okay. So I know that my diameter 1 was 2.879 inches divided by 2. And then I'm going to multiply that by W1. I cannot use the 1200. Okay, we have to change that to, now remember, the final units that we're going to use for belt or for chain speed are going to be feet per minute. So we can put this into radians per minute. Okay, we don't have to do the extra seconds. So I am going to have to, before I do that, I'm going to say W1 is equal to 1200 revolutions per minute. Okay, and I need to convert that to radians per minute. So 1 revolution on the bottom, 2 pi radians, revolutions cancel, and my W1 should be 7,539.6 radians per minute. Okay, then this will be the value that I put up there. So 7,530, comma, it's a comma, 739.6 radians per minute. Okay. So this was kind of a sidebar, if you would. Just a conversion. So my speed of my belt looks like it's going to be 10,853.3 inches per minute, right? Because this is in inches, radians times inches, radians drops out, so it's going to be inches per minute. And I want to get this into feet per minute. Okay, so that means that there's 12 inches in 1 foot. So my VC value should be 904 feet per minute, or you can put FPM. And just double check. Hopefully we got that same number. Yep, 904. Now, unfortunately, in the book, they have some typos, so we'll correct those in just a bit. Yeah, the book is the wrong number. That's something about this book. This book, I've had it since the first version. I do like the book, but there's a lot of typos. So we'll correct those in just a second then. All right, want to be sure that you guys have this. So now, okay, let's look at what's in the book. So they have the wrong radians per minute. I'm not sure why, but they do. The right numbers here, but it's supposed to be 7,039.6. Okay, and that's going to be radians per minute. Then you're going to notice that down here, because of that, that number is actually going to be, this is going to be our 10,855, I'm sorry, 853.3, right? And that's going to be inches per minute. And then 904 feet per minute. So it's just a mistake on their part. Okay. Our numbers are correct. And just want to verify, I didn't ask, did everybody get the 904 feet per minute? Show your conversions and everything, and also make sure it's readable. All right. So that means that we have the belt speed. Okay. Now, this belt speed, you might be like, well, why do I want to know that? Remember, if we look back at the bottom of page 311, right before the problem statement here, this is what qualifies the speed to let us know further down in the design process how we need to handle lubrication, okay? So in this case, we're 904, so we're not a low speed, we're a moderate speed. So in our design, we would have to already be thinking, okay, I've got to get a bath lubrication designed in there so that as this goes through and as this rotates, it's going to always be, you know, lubricated on a regular basis, just because of the speed that it's going to be going, okay? So that's why we are interested in that, that number. Okay, so if we go back to the beginning of our problem here, we have now done the belt speed, okay? Lastly, we're going to be figuring out now the center distance and the number of links that we need to get off for the total length of our chain, okay? So to do that, at the bottom here, this is step number 5. They want to determine an approximate center distance. So this is using the information of, we want this to be between 30 pitches. Okay, so our pitch, remember, is a 1/2 inch. So we're going to take 30 times a 1/2 inch. That's going to be our low center distance. And then we're going to take 50 times our pitch, and that's going to be our high value. So down here, you're going to notice that they have those in there. So we are going to, for step number 5, we're going to do our center distance. So our center distance has to be between 30 pitches and 50 pitches, right? 50 pitches. So that means our center distance needs to be 30 times 0.5 inches and 50 times 0.5 inches, okay? Inches. So that means this is going to be between 15 inches and 25 inches. Okay, so this is basically the range that we can pick because they did not give us a center distance. They didn't give us a center distance. When you're starting with a new design of equipment, this is where you start, okay? But sometimes you might already have the envelope figured out, or you have something that you have to work within, and then you're going to know that center distance, okay? So it looks like they chose between this number, I think they chose 20. Yep. So at the top of the following page, at the top of page 313, a mid value is 20 inches. So they're just picking that. And that's literally picking it out of the air. Okay, that's all for right now. So, so they said, okay, C is going to be equal to 20 inches. Now, don't put a box around that because that's our approximate. And now using that center distance approximate, we want to figure out how many links is it going to take to wrap over those two sprockets that we have and be able to and we want to know what the center distance is once we have that around there. Sorry. So number 6 here now is going to be, what are the number of links required to obtain a 20 inch? So that means that our equation, it's kind of long. I might go to the next page, I think. It's going to be this equation, sorry, right here. Okay, it's this one right here. So I'm actually going to start a new page, and this is going to be my step number 6. And this is going to be L is equal to. Okay, so we want to write that equation out in variable form to start. L is going to be equal to 2 times C divided by P plus N2 plus N1 divided by 2 plus P times N2 minus N1. We have to square that value. And the trick here is to remember to do these squares, especially the square of the pi in the denominator of that last part. Okay. All right. So because there's not a lot of room here, this is going to be the one exception I have on these two equations for center distance and for the links. I'm not going to put the units in because the numbers are going to take up enough space. Otherwise, I'm going to be on multiple lines here. So this is going to be 2 times the center distance. We said 20, right? Divided by our pitch, which is 0.5. Okay. Plus the number of teeth in 2 was 90. Plus the number of teeth in 1 is 18. Divided by 2. And yes, I'll give you the exception of putting the units in for these two equations just because they're so long. Plus, okay, our pitch is 0.5 times 90 minus 18. We have to square that value. Divided by 4 times pi squared divided by 20. Okay. And that's going to be your number of links. Okay. So see what you get for this value using those values. I broke mine into the 3 different parts. So that way you can see the numbers, how you would add them together. And then you should get a total of 137.28 links. Okay, as the number here, based on an exact 20-inch center distance. Anybody else get that number? Just want to be sure I got that too. Good, good. And it's consistent with the book. Okay. All right, now what we're going to do is we need to then round it to an integer number. Now you can round up or down. And one other rule about chain links is that they want it to be ideally an integer number and an even number. Okay, I forget exactly why an even number, but I'm pretty sure it has to do with how it goes around, that it doesn't end up on the very same tooth each and every time. Okay, it kind of mixes it up a little bit. So we are going to round this up to 138 links. Okay, 138 links. So our L is going to be equal to 138 links. So again, integer number and even, whoopsie, integer and even, a little bit over. So we're going to put a box around that. Okay. So we would count off of our, if you would, our roll of bulk chain, 138 links. Okay. And now we want to know, okay, now that we have those set up and we know the size of our individual sprockets, what's the actual center distance now? What's the final center distance? And that is going to be the even longer equation that we see right here. This is center distance actual. Okay, so go ahead and step number 7 is going to be the final center distance. I'm gonna come out of here. Okay, so again, make sure that you write your equation in variable form first. This is going to be center actual P over 4 times L. And here too, the exception is I'm not going to make you put the units in just because you're literally gonna run out of room. And then it gets hard to keep track of. Now you're going to use your actual links from above. So that's going to be the 138 for the L. I'm going to want to call it squared here with this squared. I was just checking. Yeah, the book's equation is correct here. So just double check your numbers against it and make sure you're squaring the right elements as they should be. just a little bit. On either side of it, I'm getting 22.5 inches, 22.6 inches. Let me know what you guys get if you're about the same. They get 20.187. I'm getting 22.6. Did anybody else get 22.6? Yes, no? You got what?
87.
87. That,
It's far closer than.
okay. I know, it is really long. Just double check your equation, make sure that it matches. And then I'm looking at my values in the book. So, I'm close. They get 20.187 and I've been getting the 22.6 a couple times here. I'm nice and close, but I'm not exact. I'm gonna pause this for just a second. I'm gonna do it one more time. Ben, what did you get? All right, so yeah, just double check. I had a minus here, so it came out to be 7,056. Kang Meng got that, excellent. And then you should end up with a center distance of 20.19, which, as we look back at our original problem, we started the problem a couple pages ago. That's our center distance and our number of links. So that means we got all the items that were required. Okay, so I'll leave this up here just to be sure. So with that example, that really gives us, we got a nice comprehensive look at most all of the equations for chains. So you are going to be ready now to finish up this assignment. Okay, so what we'll do next is we will look at the last 4 problems that are focused on chains that you have assigned for assignment number assignment number 5, okay? So if we go back to Canvas, all right, this gets us to the end. You're ready to do what we need to do. I'm going to go back to assignment number 5. And like we had looked at last time, the first 4 problems dealt with belts. Okay, so we went over those in detail the last time we were together on the first lecture, if you would. And now we've got these last 4 problems that you need to complete that deal with chains. So let's go underneath. And starting on page 314, I'm sorry, 1118 is in the first column here. And in this case, it says you have a gear motor operating clockwise at 220 RPMs, is coupled through a number 40 chain to a liquid agitator. The drive sprocket has 19 teeth, and the mixer sprocket has 50 teeth. Determine the speed of the driven sprocket, the chain speed, VC, and the recommended lubrication method. So once you know what your VC is, you then are going to be classifying it as that low, moderate, or high speed, and then identify the lubrication that would correspond with that. So that's your first problem. Your second problem is going to be 1120. Here we have a shaft of a gearbox is coupled with a number 100 chain, rotating a drive shaft for a pulp screen at a paper producing plant. The screen drive shaft rotates at 250 RPMs. The drive sprocket has 25 teeth. The sprocket on the mixer has 76. Determine the speed of the drive sprocket. So that's going to be W1, how fast that needs to go, and the chain speed, as well as the lubrication recommendation method. Okay, so again, once you know what your VC is in feet per minute, you are then going to determine if it's that slow, moderate, or high speed, and then corresponding lubrication. The next one you have is going to be 1122 up here. 2 sprockets, they're both number 80 chain, have 19 and 64 teeth, so they've got that figured out for you. The chain itself has 140 links. That's going to be the length, okay? Determine the pitch diameter of each one of the sprockets, the center distance, and the angle of contact, okay? That's going to be that angle of wrap over the smaller sprocket. So that'll be probably your theta 1. Also compare the center distance to the ideal range, okay? See if it's within there or outside of it. You don't have to change anything about it, but just compare it back to it. So make sure you answer that last part. And then the last problem that you have is going to mimic pretty closely the last example problem that we just did. We have a chain drive is desired for a corn picker to couple a hydraulic motor and a drive shaft. The 30 horsepower motor will operate at 550 RPM, and the drive shaft must operate as close to 100 RPMs as possible. Select an appropriate chain size, commercially available sprockets, and the number of links in the chain. Also calculate the actual chain speed and the chain and the center distance. So just like that last problem that we went through. Okay. So with that, that brings us to the end of module number 5. Okay. So, so does anybody have any questions as you're looking here? Couple reminders on the assignment, just like on our practice problems. Number 1, I'll wait till everybody's ready because I want to make sure everybody knows this. You have to write the equation in variable form, okay? Just like we've been doing as we've been going along. So for instance, okay, when you are calculating something, you have to show it in variable form first, then either rearrange, and then lastly, put your values in with units canceled. The exceptions to the units are going to be those last 2 equations that we looked at. So for the length of the, or for the number of links and the length of chain, and for the actual center distance, it's going to get too crazy with units. So I'm fine with you not putting them in for those 2. Okay. So make sure you do that. Additionally, I have to be able to read it. I've got people still that I have to kind of squint and look. I'm just not going to do that. You guys are second-year students. I have to be able to read what you write. If you're like, well, that's just how I write. Okay, then you just get points off. I'm not going to try to figure out what you're trying to tell me. This is a communication tool. You need to be able to let people know what you got for your values, okay? Units and everything except those two equations, like I told you. Make sure that those are canceled out and everything is coming out correctly. And then boxes around your final answers with the variable and the final units. So, for instance, I don't want to see just a number with units with a box around it. You need to tell me what variable you're solving for here. So in this case, it's D1 is equal to. Does that make sense to everybody? Okay, because I'm seeing a lot of this. All right. Now remember, you might say, well, she's so picky. What's my reason for being picky on the assignments? I think we talked about it last time. Why am I picky on the assignments that you hand in? No tests. You guys don't get a test in here. So you are going to have to pay attention to these details when you hand things in. I want good quality second year engineering student work. Okay, that's what I'm expecting from you. All right. So that's why I'm a little on you about formatting. Okay, a lot on you about formatting. Pay attention to those details. They are important, and they're not just because I'm saying so. These are things that are expectations when you're out in industry. Your boss, your companies are going to have ways that they want you to do things. You have to be able to adapt to that. Okay, and this is one way that we're getting you ready for that. All right, so if there aren't any questions, then you have the rest of the time to work independently on this assignment, okay? Don't go anywhere, all right? I am going to stop the recording at this time.